print the front side, again using a silver paste. Sorry. So then you need to basically, to make good contact, you need to actually do a high temperature process. So this is typically around 750 to 800 degrees centigrade. You treat this whole thing, and then you get your solar cell. Okay, so I'll spend a couple of more minutes on this thing. What do you get out of this? Maybe before that, if anybody has any questions. So we can spend maybe about 5 minutes to answer questions. Anyone? Hello? Hello?
Yes, sir. Yes,
Sir,
sir.
I think
Yeah,
Yes, sir.
if anybody has any questions, you can ask.
Yes, sir. So, audience, like participants, any queries? Just 2 minutes. If you have questions, you can ask to sir.
Sir,
Yeah, please.
sir, sir,
Yeah.
we can prepare material by magnetron sputtering also, either a DC magnetron sputtering or RF sputtering. These silicon cells coating.
The silicon wafer is actually produced by a completely different process. So, the silicon is produced from silicon dioxide, which is, so you take high purity sand, okay, quartzite. So this is a mineral of silicon, and then you are purifying, so reducing it, purifying it, and then make crystals out of it. So
Sir,
that's
sir.
typical process. And then so you can make these layers. For example, you have several thin films. For example, here you have a silicon nitride, oxide, right, and aluminum, and so on and so forth. So typically you use what is called a PECVD, plasma enhanced chemical vapor deposition, for depositing the top silicon nitride layer. And aluminum oxide is also deposited by PECVD or by atomic layer deposition. Sputtering can be used, but then that's not an industrial process because it's a quite expensive technique. Okay.
Okay. Sir.
Yeah, but you can definitely make solar cells using sputtered oxide, silicon nitride oxide, and so on. So we had, for example, I had a PhD student who looked at sputtered aluminum oxide for passivation of silicon. So this can be tried, but nobody uses it commercially. Any other question? Okay, so this is a typical process, right? Anybody wants to ask 2 more minutes, maybe? Can.
No, sir. We can continue, sir.
Okay, good. Okay, so if you make a solar cell, okay, so this is, you can see here, this is essentially a diode, right? It's a P-type silicon, N-type here, okay? So it's a PN junction diode, right? And I hope that many of you who have this background in electrical engineering and electronics would easily understand the PN junctions. But then, I see that now even in +2, 11th and 12th, students actually do learn about diodes, though they may not really know a lot about PN junctions, but they actually have learned about it. So this is really a diode, but then we talked about this industrial scale things are like 6-inch by 6-inch, very large diode. But it is processed and made in such a way that light absorption is actually optimized. Okay, so it's not just an electrical device, but it's an optoelectronic device. So that means that you have to do certain things to ensure the almost all the light that is incident on the solar cell is enters the solar cell, and then they get trapped inside so that they don't escape before they are absorbed. So that is the major difference. Now, so this is a diode characteristics, but it's kind of flipped over because that is kind of convention in the PV community. So if when you shine light, this is a diode characteristics. Usually we draw this part on this side, okay, and this is your forward biased diode characteristics, right? So this is if you have a dark thing diode where you are not shining light, it would go like this, right? Yeah, and the reverse bias, it will go like this. Okay, breakdown. Okay, because we have just multiplied the current with -1, so that's why it looks a little bit like this. Now, what is this thing? So we can see some parameters that are defined here. Okay, and an equation. So the total current that is flowing through the diode, this solar cell, has major two components. This is something that you would immediately recognize if you remember the diode theory. So this is the diode current voltage equation. Okay, this is the voltage across the solar cell, and then IL is the current produced by the light falling on the solar cell. Okay, so you can now see that the short circuit, which means that if you take two terminals of the solar cell and short circuit, the front side and back side terminals, right? In short circuit, a current will flow because this voltage is 0, so this would be 0. A current would flow. That is purely the current produced only by the this. Now a current because from the light. Okay, so now if you connected load to the two terminals, this current will flow through that load, and that will produce then a voltage, right? Because the current is flowing through a resistor, for example, so you would get a voltage. Okay, as a consequence, there is a voltage that is now across the solar cell, and that means the voltage across your PN junction diode. So a current will start to flow through the PN junction diode. So the current that is available to drive the external load would actually start to decrease. Okay, so this is the idea. And then when the external load becomes infinite, so essentially it is an open circuit, no current will flow, and this is called the open circuit voltage. So this is a short circuit current, open circuit voltage, and you can actually rearrange this equation. So current is set to 0 here, total current, and then from that you can calculate what is called the open circuit voltage. It's just a rearrangement of this equation in this form by setting I is equal to 0. Okay, so these two are very important parameters for solar cells. We will see how this is being measured. So very important thing. Now people talk about what is the efficiency of a solar cell. Okay, so this is a very important thing. Efficiency, how do you define efficiency of any system? So the output divided by input, right? Now a very important thing to consider here is what should be the input. Okay, so that's a tricky question, because if I place a solar cell outside in the sun, in the morning the sunlight is fairly low, and then it increases during the noon, it becomes very high about 1 o'clock or something, and then towards the afternoon, evening, it is decreasing. In the night there is no light, sunlight, right? So this means that the solar energy that is available for conversion is actually changing with time, and it is not the same in India, meaning if you go to the north and to the south, these things are going to change. And then depending on the cloud and other things, a lot of changes, right? So you need to then define, if I want to have in China somebody is making solar cells, Germany somebody is making, India is somebody is making, and they all claim that it is 20% efficiency. So then the input should be identical for all these measurements. Okay, so there is an international standard for which defines what should be the light spectrum of light that you should use. So this is this, for example, this blue curve that you see here is called the AM 1.5G. So AM stands for air mass, 1.5 is some air mass of 1.5, and then you have G is global radiation. Okay, and this is compared here. AM0 means that just outside the atmosphere of Earth you would get this red. Okay, and then of course there is a significant reduction here, mainly because of absorption by ozone. And then in the atmosphere you have moisture, H2O, and then oxygen, carbon dioxide, and so on and so forth. So that causes these drops here at various wavelengths. Okay, and this is also agreed internationally to be 1000 watt per meter square AM 1.5G. So this is what people use for measuring the solar cells to find out the efficiency of the solar cell. This is very important point. Okay, and if you are to use a black body, for example, this is the ideal black body radiation for 6000 Kelvin. Okay, now this is a typical solar cell, slightly older technology. You can see some of the features here, the current. So this is about, I think, a 5-inch by 5-inch solar cell. Current is actually about 5.5 amperes. Okay, and the voltage is here, open circuit voltage is 0.6 volts. And you take the product of current and voltage, so then you get this red curve, so that is the power. Okay, so the power shows a peak. Okay, so it's understandable because here the voltage is 0, right? Current is high. Here the current is 0, voltage is high. So both these ends will be 0, and then it peaks somewhere here. And this is the point where the power is maximum. So it's a maximum power point, and the voltage, you would really like to operate the solar cell here, but because that is when you can extract maximum power out of it. Okay, illumination is the same. Only thing is that the voltage has to be selected. So you can see that this voltage, this device, even though it has about 0.6 volts as the open circuit voltage, you can extract only about 0.52 volts at the maximum power point. And the efficiency is then defined as this maximum power, right? PM divided by P incident. So P incident we have seen 1000 watt per meter square. And the spectrum and all these details are specified in an international standard, IEC standard 60904. Okay. So you have the PM is a product of the current at this point, right? This current and the voltage at this point. And then you can express this thing in terms of what is called the meaning ISC, the short circuit current and open circuit voltage. And we had also seen, we'll see this, what is this fill factor? FF stands for fill factor. So fill factor is very simple. So basically you can construct a rectangle, okay, where one side is the VOC, okay, the other side is the ISC. So you can draw a rectangle like this, right? Okay, so now this curve is of course filling a smaller area than this rectangle. Let me see if I can draw this here on this screen. Then, okay. So you can actually, what I'm saying is that you can draw a rectangle like this, right? Yeah. A rectangle can be drawn. So you can find the area of this rectangle is nothing but ISC times VOC. Okay. How much of this area is being filled by this black curve, right? Yeah. So that's called the fill factor. Okay. So typically the fill factor is 80%, 0.8 for a silicon solar cell. And it's a typical number. And higher the fill factor, better your solar cell. Okay. Okay. Now let me do this. Okay. So there are some efficiency limits, fundamental efficiency limits for solar cells, what is called a single junction solar cell, the solar cell that we have seen so far. And they come from these factors, so optical losses. Okay, optical loss means that this is the front side of the solar cell, let's say, yeah, semiconductor, and this is the back side. Okay, so the light that is incident, part of this, a small fraction would actually be reflected back. Okay, so you lose some light, yeah. And then there is a transmission loss. So for example, in silicon, if you have 1100 nanometer wavelength light, we have seen that it requires something around 620 micron thick silicon to absorb 64% of that light. Okay, but if I'm using a 200 micron silicon thickness, right, it is possible some of the light would actually escape through the backside. Okay, so the solar cell that we have seen, there is aluminum on the backside, right? So this light will be reflected, and then it will travel back, meaning to the front side. So during that time, it can also be absorbed. So the path length for this reflected light would be totally 2 times the thickness of the silicon wafer. Okay, and it can escape also from the front side, right? So optical losses are a part of this. So a small fraction will be lost. So this has to be reduced by proper design of the optics of the device. So for example, texturization, backside reflector, and increasing the internal reflection, and so on and so forth. Second is thermalization loss. This is an interesting thing. What does it mean? So you can see that, this is a band gap of the semiconductor, and we said silicon, the band gap is 1.1 eV. On the other hand, if you take, for example, a 600 nanometer wavelength light, okay, 620, for example, nanometer wavelength light, which is red light, right? Then the photon energy is 2 electron volts. Okay, so the photon has higher energy than the band gap of the semiconductor. As a consequence, an electron that is excited from the valence band to the conduction band would actually have 2 electron volts. So 1.1 here, and then 0.9 electron volts is excess. Okay, so what happens is that this would go through collision. So the electron would collide with the atoms and other electrons in the system, meaning in the material, and then lose this part of the energy by thermal energy. So the solar cell will heat up. Okay, and then it comes down to the bottom of the conduction band. So this is thermalization loss because it's lost to the crystal or the solar cell as heat, and you only have the remaining part. So this much energy is lost anyway. Okay, you can't do anything about it. Okay, this is fundamental. Okay, now we'll see how this can be reduced in a later part of this thing. Now there's something called free carrier absorption. What does it mean? That an electron which is already in the conduction band can also actually absorb a photon, and then it actually has higher kinetic energy, but then it would also collide with the crystal and lose that energy by thermal means. So this is a free carrier. This was not a free carrier. You actually excited it to become a free carrier, but here it's already in the conduction band. So free carrier would absorb, this is lost. Okay, so these are some of the fundamental losses in a solar cell, and this leads to problems. For example, if you can see here, this is your solar spectrum AM 1.5G, right? And then if I take silicon, so this is the maximum wavelength that silicon can absorb. So this part of the spectrum is lost. You can't absorb this light. Okay, and out of this, you can see here it actually 100% can be absorbed in theory, but then as you go to lower wavelengths, of course you have more fraction lost, because as you're going in this direction, right, wavelength is decreasing, the photon energy is increasing. Okay, so you lose more and more energy because of the thermalization losses here. Okay, so the maximum you can actually achieve using a silicon solar cell is what is shown in this red. This is the sun spectrum, and this is what you can extract using silicon, for example, or any single material. For the difference will be if you take gallium arsenide, for example, that would absorb from 870 nanometer or something. And then, of course, this part, the thermalization loss will be smaller because the band gap is slightly larger for gallium arsenide. Okay, so now there is this thing, this basically these factors set an upper limit on what is the maximum, meaning the maximum conversion efficiency you can achieve in a solar cell. So this is called a Shockley-Quasar limit. It's William Shockley, so he and his collaborator calculated what can be the maximum efficiency of a solar cell. They actually plotted this, okay? The efficiency as a function of the band gap, okay? And if you want to read more about this, how they actually got this, there is this paper 1961. They actually calculated this as a function of band gap. So you can see the maximum thing is achieved around 1.4 eV, which is the band gap of gallium arsenide. Okay, silicon, this is the band gap of silicon. So you actually can get up to 30.3% as per Shockley-Quasar calculation. And then in 2013, the scientist Richter and his collaborators calculated, recalculated this, and they did what is called a reassessment of the efficiency by considering some of the other losses. They came up with this number 29.3%. Now, what is the record efficiency that has been demonstrated for silicon solar cells? So this is done by a company called Kaneka in 2016. And they demonstrated an efficiency of 26.7% conversion efficiency. You can see now what is being, most widely manufactured solar cells in the market. It's in the range of 18 to 20%. So this is a slightly complex technology. It's not very cost effective. But then with cost-effective technology, you can make something like this, 18 to 20%. So these are some of the publications from where we have taken this data. Okay. Now, if you look at advanced silicon solar cell, so you can see here, this is the PERC solar cell that we had already discussed. Okay, so people have achieved up to 24% efficiency using this structure. Okay, and now you can do what is called interdigitated back contact cell. What it means is that, you can see this is a silicon, N-type silicon. Both contacts are on the backside in this. Okay, so you have a junction. So this PN junction is on the backside. Yeah, both contacts on the backside. What does it mean? On the front side, it will just look like a black thing, no metal on top. Okay. So the light that, in this, the light that is falling on the metal will be reflected back, right? Because metal usually reflect light. So you cannot get this part of the sunlight cannot be converted to electricity because it's reflected back. In this case, that is avoided. Light that is falling on here would actually be going into the silicon. Okay. So this is called back contact cell, interdigitated back contact cell. So you have two types of contacts, one that is shown here as in the front side. So one contact here, another type of contact here, and then next would come this contact right here. So interdigitated contact. So this is a slightly different architecture where people have approached, 26% has been demonstrated very recently in 2021. This paper came out in 2021. And this is actually using something similar to this. Okay, only thing is there is some difference here. Instead of aluminum oxide and so on and so forth, you see a polysilicon and oxide layer. Okay, so this is called a TOPCon architecture, and this is very recently published about 4 centimeter square area, 26% efficient solar cells. And this is the record efficiency solar cell, which is called heterojunction with intrinsic thin layer, 26.7%. Again, this is an interdigitated back contact cell. Both contacts are on the back side. Okay, here something that is being used is amorphous silicon. So this is silicon, crystalline silicon, but this is amorphous silicon. here as well as on the back side. And then you have an electrode pattern for external connection to external circuitry. Okay, so this is the highest efficiency silicon solar cells achieved so far. Now, here, all these things we have seen, the light can enter from the front side, back side is all metal. Okay. But these technologies have something here again, backside is all metal. Here you have something different where the space between this can ideally be used for letting light in. Okay. But usually the device design requires that, these contacts are closely spaced. So there's hardly any space in between. But this one, for example, provides an option where you can actually let the light in through this backside between these two contacts. So such solar cells are called bifacial solar cells. Presently, this is achieved only in silicon, okay, at commercial scale because that is relatively inexpensive to make. So you have contacts on the front and side, back, and then in between space is used for letting light in from the front side as well as from the back side. Okay. So we'll see this, what is the application of this in the field. Okay. So now we have the silicon photovoltaic module. Why do you need what is called a module? This is because we discussed that, and we have seen that what you can get from a single solar cell, irrespective of the area, is something around 0.5 to 0.6 volts, okay, from a silicon solar cell. So if I want to have some useful device, then I need to connect many of them in series, okay. So these are all series connected solar cells, okay. You are basically connecting them in series this way or this way. Yeah. So you have the series connected solar cells, and then of course you are talking about silicon nitride, and so on and so forth. These are not very robust materials. If you expose them to sunlight and rain and so on and so forth, they can degrade. Okay, and you have a silver metal on the front side, aluminum on the back side, and so on and so forth. So it's a little bit messy to put this into to expose them to the elements. So what you do is you package them into a thing like this. Yeah, it's like, you also might have seen ICs, right? You can't usually see the silicon chip in an IC because they're all packaged inside a plastic package or something like this, right? So here, this is, this is a typical packaging thing. You have front side glass and then an encapsulant. Okay, so this would be the closest thing to the solar cell, right? And then you have on the back side a backside encapsulant and a backsheet, polymer backsheet. And of course, there is an aluminum frame. So this whole thing is packaged into to protect the solar cells from air ingress, water, also mechanical shocks and so on and so forth. And there is something called a junction box. This is basically some basic electronic components, again diodes, to protect the solar cells from partial shading and other issues. This is a slightly different realization of this, pretty much same as what you have here, but what you find here is on the back side, instead of using polymer, use glass. Okay, so this is typically used in the case of bifacial module, so that you can also let light into this. Okay, so this polymer backsheet is typically not transparent. Of course, these encapsulants are also polymers and they are transparent. Okay, just a moment. Okay, so now if you take the bifacial silicon module, this is an interesting technology, and if you install this bifacial modules, so you can see these gaps between the cells here. Okay, and through that light can go in. Okay, so light that is falling on the front side, most of it would be absorbed by the solar cells, but if there are gaps, that will actually go through. Okay, and also on the sides, anything, if it is the photovoltaic module, for example, is installed on a rooftop with some aluminum structures and so on and so forth, what would happen is that you also have a lot of space around it. So the light that is reflected from the backside can be absorbed by the backside of the solar cell. So this light is called albedo, okay. So typically the albedo is 20% of what you see on the front side. So by this technique, you can actually increase the energy converted into electricity. And people are using it in very innovative ways for various applications. For example, you can put this and light, part of the light would still go through, and then you can do farming, for example, under this. So this can be used in greenhouses, and you can be used in ponds, for example, because if you install floating solar things, one of the concern is what would happen to the plant growth, fish, and so on and so forth in the ponds or lakes and so on. So part of light can actually go in. You can design them, the spacing can be designed and so on and so forth. So there's some very active field of research, what is called agrovoltaics, where this can find a lot of applications. Okay, and of course, higher energy, but of course, the thing is that, this albedo would depend on the reflecting surface. So if it is white, like snow and so on and so forth, that's good. But then many places, the sand may be blackish in color, so it may not be so good in such places. Okay, thin film photovoltaic technology, that actually is realized in a slightly different way. So you have a glass substrate. You start with a glass substrate. This is actually transparent conducting oxide, TCO. Okay, so that is deposited on it. So it is transparent, but it is a conducting metal oxide. Okay, so this is what is, and then you are making some openings in this using laser deposition of absorber layer. So it can be cadmium telluride, for example, amorphous silicon. Okay, and then you're going to make some cuts in the absorber layer and deposition of the back metal. So this is where you're going to have absorption, and this is of course transparent. This is glass, right? So light can actually, this is made upside down, and you flip it over, and then light can enter through this, and it goes through this and enter here. Okay, and you have a contact on one side and the contact on the other side, and you have your solar cell that's actually used for this application. Meaning, so you can have the current flowing through this. So here there is an opening made so that the current, it's not short circuited, right? At least here it looks like the front and this is the front metal and this is the back metal. They're short circuited, but that is being avoided in this case. So the light will basically, it will go through, current will flow through this, right? And you get a solar cell. So the advantage here is usually, the thing is that this is thin film, very thin, 1 micron, 2 micron, and so on and so forth, compared to 200 microns for silicon. So it needs much less material, and you can use many various deposition techniques for making these thin films. Now, photovoltaic modules made, the crystalline silicon, they typically look like this. These are the wafers, right? And so you have the bus bars and so on and so forth. This thin film. Here again, you may actually notice some lines here. So these are the metal lines, okay, scribe lines and so on and so forth here also. So this contains also cells, small cells connected in series. But we are using a transparent conducting electrode for this. Yeah, so it's not very visible. Okay, the metallization, unlike here where you use silver, which reflect. In this case, you are using a transparent conducting oxide. In fact, one of the major cost component in this is actually the transparent conducting electrode. Thin film technology, so we have cadmium telluride, CIGS, so copper, indium, gallium selenide, group 3, 5, so for example, gallium arsenide type of solar cells, amorphous silicon and associated technologies. dye-sensitized organic perovskites. These are all thin film technologies. Okay, so we can take maybe a question or two if anybody has what we have discussed so far.
Sir, all the participants, you can unmute. If you have any doubts, you can ask, sir.
Any questions? No questions? Okay. One Mr. Kiran was asking some question. Hello? There is some questions being typed in chat box.
Yeah.
Okay, okay. So what are the efficiency of mono and bifacial module technology? We will come to that in a moment, okay? I'll show you. Yeah. Anyone else? Any questions? So the efficiency is typical efficiency numbers I'm going to show you in a moment. Okay. Anyone else? Any question? Okay, if not, we will go ahead. Okay, so we have this, just a moment. Okay, so this is, just a moment, I'm trying to get rid of this chat window. Okay. Yeah, so this is, you know, a very crowded graph, and so it's not a very good thing to show in presentations. But what does it show? Actually, it shows a history of the efficiencies, record efficiencies reported from 1970s. Okay, so these are different, you know, technologies. So, for example, crystalline silicon would be somewhere here, for example. Yeah, crystalline silicon is something like this, right? And then so it's 2016 or so, Kaneka, they reported this 26.7%. Okay, and then you have other technologies, for example, these are all crystalline silicon, various types of crystalline silicon. And then you have thin film, CIGS, cadmium telluride, and so on. So cadmium telluride is somewhere here, for example. Okay, and CIGS is also here. CIGS, this is CIGS. It has actually reached a higher efficiency, 23.4, and so on. So this is published by this National Renewable Energy Laboratories, NREL, and you can see this in Wikipedia. So you just go to Wikipedia and look at solar cells or photovoltaics, for example. You will find this. They keep on updating it every now and then. Whenever there is a record efficiency cell announced corresponding to any technology, you get this. Now there's something called multi-junction solar cells. Okay, and they are also more than one junction. Okay, we'll see that why, what is the advantage and so on. So you can ideally get you know, much higher efficiencies with this. So the highest you know, reported so far is 47.1%. Okay. So it's good to actually keep tab of this, you know, to see what is the efficiency. For example, these are present record cell efficiencies, terrestrial, which means that for applications on the Earth or Sun at one sun irradiation. So 1000 watt per meter square, what we discussed previously. And this is, based on the data published in this paper. So there's something called solar cell efficiency tables. The latest version was in November 2020, published in this journal called Progress in Photovoltaics. So silicon crystalline, this is the area, okay, and it's a very interesting graph. Area of the cell, okay, and this is the efficiency. So we have seen silicon, crystalline silicon, right? 26.7% efficiency, and this is multi-crystalline silicon. So this is a different type of crystalline silicon, and it has lower, slightly lower efficiencies. Okay, 24 point something, and then gallium arsenide, you can see here close to 30%. Okay, and indium phosphide, CIGS, perovskite, cadmium telluride, organic, dye-sensitized amorphous silicon, and so on and so forth. So now an interesting thing is that this is an important distinction. So you can see here the area of the cells are very large compared to what you have here. Okay, so that's a very important thing, because if you want high efficiency and large area, then the technology to go for is crystalline silicon. For example, cadmium telluride, you can see here, this is the cell. These are cells, 1 centimeter square area. CIGS 23.5 is the highest efficiency at the cell level. But if these are thin films, and typically deposited by various thin film deposition techniques like CVD and so on and so forth, sputtering and things like that. So the problem here is that the defects in those materials, when you deposit by these tricks, are actually fairly large. So if you want to make larger area solar cells, then more defects will be there in this, okay, which means that the larger area devices would have lower efficiency because of the presence of defects. Crystalline silicon, on the other hand, you can actually make large area without many defects. So that is one of the major advantages. And here you can see the module. So you construct modules out of this, and that gives you affirms the previous thing, that crystalline silicon still has fairly high efficiencies, and you can see the module area can be very large. On the other hand, CIGS, cadmium telluride, these are okay, but not as good as crystalline silicon. Okay, so that is one thing. So these are basically high area, meaning high efficiency, large area modules that you can get. Gallium arsenide area is much smaller, okay, 1/10 or even smaller than that. Okay, so you can see that this was close to 30% for cells when it was 1 centimeter square, whereas at 1000 centimeter square it is now about 25%. Now, a very important thing is that actually, if you want to design a photovoltaic system, very important thing is the temperature coefficient of power, which means that basically this is in parts per million per degree centigrade. So what it means is that we are actually measuring the efficiency. So when you say 20% efficient cells, this efficiency is measured at a temperature of 25 degrees centigrade. Now, and when you increase the temperature by 1 degree centigrade, this would actually, the power, for example, would actually decrease by, for silicon, about 0.4%. Okay, so if you take a 100-watt photovoltaic module, and then that 100-watt is actually for 25 degrees centigrade. Okay, and then if you say, okay, I want to operate it at outside temperature is 50 degrees, meaning let's say 35 degrees centigrade, but when I place this in the sun, the temperature may go to 50 degrees centigrade, for example, depending on the wind and various other parameters, 50 degrees centigrade. So 25 was what the thing was specified for. Now you are increasing this by 25 degrees more, right? So every degree centigrade, there will be a 0.4% reduction. So if you now take it 0.4 into 25, so that would be actually about 10% reduction. So 100-watt module would give you now only 90 watts. Yeah, so this is the point here. The performance will decrease with increasing temperature. So this is for silicon, for example, about 0.4, okay, meaning this is in parts per million. So if you convert it to percentages, 0.4 crystalline silicon. On the other hand, if you look at cadmium telluride, it's typically smaller. Yeah? The average value is about 0.25. Okay, so thin film may have an advantage at higher temperature because you started off with, let's say, 18% efficiency for cadmium telluride. Here 20% efficiency. These are specified at 25 degrees centigrade, but in the field, if they are both operating at 50 degrees centigrade, there may not be much of difference between the two technologies in terms of the power output. Yeah, because power output per unit area, because the power output of this would have decreased more significantly compared to cadmium telluride because of the different temperature coefficients. Okay, so now if you look at the market share of various technologies, so these are two major technologies, meaning thin film technologies. Crystalline silicon, about 95% of the overall market. Commercial modules can be as good as 19% efficiency. Cadmium telluride CIGS, about 5% market share, and efficiency in the range of 16%. So this is, considering this fact that, okay, they have higher efficiencies, and also you can get larger modules and so on and so on. Cost is actually also meaning somewhat lower for crystalline silicon technology. Okay, then we have seen this, what is called the Shockley quasar limit multi-junction solar cells, right? Absorber 1, 2, 3. So what does it mean? So we had in silicon, the silicon was the absorbing material. So silicon would absorb the photons. Okay, and we had seen what is called a thermalization loss, right? If the photon energy is much larger than the band gap, the excess energy is wasted. Okay, so what we are doing here is actually use 3 different semiconductors with 3 different band gaps. Okay, so light enters from here. Yeah, so that is the important idea here. You would actually have the light entering from here, and the first absorber would actually have a larger band gap, okay, than the second absorber, and second absorber would have smaller band gap. What it means is that the larger energy photons will be actually absorbed here, okay, and then these small energy photons cannot be absorbed in this material because the photons have smaller energy than band gap of this. So it will be transmitted. So those would be absorbed here. What cannot be absorbed in this material will be transmitted, will be absorbed here. So there are 2 problems that we are solving in this. So you can see this is your single junction silicon, for example, right? We had 2 problems. One is that this wavelengths could not be absorbed in such a solar cell because the photon energy was smaller than the band gap of the semiconductor. Okay. So in this thing, so if, for example, here this is one typical example of a triple junction solar cell. So 3 different materials. Now you can see that the different absorbers actually absorb light at different wavelength ranges. Okay, so the germanium is in this particular design is absorbing this part of the spectrum. Okay, and gallium indium arsenide this part of the spectrum, and gallium indium phosphide this part of the spectrum. So the other thing is that, compared to this, let's take 500 nanometers. So this much energy is lost basically in thermalization losses. But here the band gap of this material is higher, 1.7. Okay, so that means that you have about 800 watt per meter square per micrometer is absorbed. Here it is only about 500, right? So this is only about 500. Yeah. So you have lesser thermalization losses, and then you are actually harvesting larger spread of the spectrum, which means that ideally this can have much more, meaning this can be much more efficient. Okay, that's basically what is done here. Shockley-Queisel limit is actually broken by using multi-junction solar cells. But then the difficulty is that this is one of the typical examples of a 39% efficient multi-junction solar cell, 3 materials. You can see here this is very, very complicated. Okay, so you have 3 layers, right? These are the 3 layers that we are talking about, right? Actually, you also germanium. So this is your germanium, and this is your materials for absorption of the other part of the spectrum. But then there's so many other layers required for reducing the resistance between the materials, the recombination of this electron pairs in the interface, and so on and so forth. This is very, very complicated. So you can count here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17 layers are required in this solar cell. On the other hand, we have seen this silicon solar cell, right, where we had silicon and silicon oxide on both sides and silicon nitride on the top and the bottom aluminum oxide. So we had basically 4 materials, but here 17 materials. Okay, and when you're depositing this by many different techniques, so the possibility to get defects in this is fairly large. As a consequence, you cannot make very large area of this, and cost is going to be enormous. So that is actually one of the major issues, though you can ideally get 39% efficiency. Now, what is the solution? If I have very high efficiency solar cells, I want to use them. So I can, my constraint is that I can only make small solar cells of very high efficiency. So what we do is, this is a clever design. So you place the solar cell and then you have a lens. Okay. What does this lens do? The lens is designed in such a way that all this light that is falling on this, right? So lens area is much larger than the solar cell. And you will make sure that this light is actually concentrated, right, using this lens onto the solar cell. All of this light would actually be falling on this small area of this. So this is called concentrated solar cell. Okay, and we have all played with lenses when we were small children, and what is the consequence of this? This can actually heat up to high temperature. So we used to burn like paper and so on, right, by using lenses. So it can really go to fairly high temperature. Now the concentration is just this, the area of the lens divided by the area of the cell. So you can get very high efficiency, concentrations are possible, but there are complications here. For example, so this is a typical photograph of a typical concentrated photovoltaic module. So you can see it's fairly complicated compared to a thing that we have seen. So here you have the solar cells here, and these are the lenses. Okay, these are the lenses, and then this is a heat sink. So you need to basically keep the temperature within a certain limits. So you need a fairly expensive heat sink to make this a viable technology. Okay, so you can see the record efficiencies are really very impressive. 47.1% is the highest. Various technologies, and the area of the cell is very small. Okay, so in the case of silicon, we have seen like 200 centimeter square and so on and so forth. Here, this is really tiny. Okay, here also, you are talking about concentration. So these numbers here, these are concentrations. Okay, so the lens area in this case would be 500 times of the solar cell area. Yeah, so that's what it means, right? Okay, now one of the challenge is this. Okay, so the cost is one thing, but there is one more challenge. What does it mean? So here, what we have assumed is that this is your lens, and the incoming light is incident perpendicular to this plane, right? That is what we have assumed. But natural sunlight is not like that. Yeah, so this is called direct sunlight, but you also what is called a diffuse component of light. This comes from, as the light enters the atmosphere of Earth, it's actually going through this atmosphere which has dust particles, moisture, carbon particles, and so on and so forth. So the light will be scattered. Okay. So not all these rays are going to come down straight from the sun. They will be actually coming also at different angles. So the two components of light. So this is basically random directions. They can come in random ways. So this is called diffused component of light, and this is called the direct component of light. Okay, so you can see that this is again in the standards these are defined, and the global we have seen AM 1.5 G global. Global means the sum of both the direct and diffuse components. Okay, so you have the direct component is what would be focused by the lens. You have the diffuse component. For example, this is one example which is incident at an angle, because this may be reflected from scattered by a particle in the atmosphere that would not fall on this solar cell, so it is lost. So this is not a viable or actually good technology where the sunlight contains a large fraction of diffused component. Okay, so for example, in India, our air has a lot of dust, especially during the summer months, and diffuse component of light is significantly higher compared to many other places. Okay, so this is the technology is costly. It has these kind of challenges and so on. So it is not a very commercially successful technology for terrestrial applications, but for space applications, concentrated this kind of technologies are used. There, in the space, the temperature of the surrounding ambient is very small, so you don't really need very expensive cooling, and then you don't have to worry about scattering from dust particles and so on and so forth, because just outside the Earth's atmosphere, the density of those particles, it's almost empty space, right? Meaning you don't have as many particles to scatter light. So space missions, they use these technologies because their high efficiency can be fully utilized, and the cost is not necessarily a constraint. Now, another system is something that is being used is tracking. So what does it mean? So this is my photovoltaic module, for example. It is fixed, okay, but sun is moving like this, right? Yeah, morning to evening. So what do we do? So this is your east, and then it goes like this, right? East to west. So in the tracking system, what you do is you are actually rotating this module so that it is always facing the sun. Suppose the sun is here, right? You would actually rotate this. So there is some mechanism that will basically detect. There will be a sensor what detects this orientation of the sun, and then there will be some motors that would be activated to rotate the photovoltaic panel. So this is called tracking. Okay, it's tracking the sun. So single axis tracking means that morning to evening, this is actually being tracked. Dual axis means that also there is a seasonal variation, right? June to December, for example, you will see this thing happening, right? And meaning throughout the year, there's a small change. that we usually don't recognize from day to day, but from a different season. So you can also have dual axis tracking. This is one photograph of a concentrated PV system where it is mounted on a single pole, and it is done dual axis tracking. This is very critical for concentrated solar because we always assumed in that the sunlight is coming directly perpendicular to the surface of the lens. Okay, so but also without concentration also you can actually get more energy. So this is an example. This is from a real installation. So you can actually go to this website, very nice. You can download a lot of data and do some analysis and so on and so forth. So I downloaded the data. So they have this cadmium telluride thin film modules, 630 kilowatt peak installations for this year, 2000. Yeah, this is a typical day. For example, this is a fixed tilt. Okay, this part. Yeah, single axis gives you more energy, right? Total energy. Okay, it's broad. Dual axis gives you slightly more. Okay, so there is a significant improvement, increase in the energy, fixed tilt and single axis. So as a consequence, this technology is now quite very common in large scale installations. Dual axis is a small increment, so that's not really meaning you need a structure which is strong, and you need to rotate this, so there must be some motors, controls, and so on and so forth. So obviously the system price will be higher, but then this 14% increase actually still makes it worthy. Okay, so you can, the cost of the incremental cost for all these things, motor and all these things, is actually smaller than this increase in energy yield. Okay, so you can recover those costs within a short period of time. So that is what it is. But this is still not economical. Okay, so this is what I wanted to present. So give you, the idea was not to go into a lot of details, but rather to give you an overview of this technology. What are the different options being explored, and what is the status in terms of efficiency that is achievable or achieved so far. Okay, so I would like to acknowledge NCPRE for funding, the which is funded by MNRE, Government of India, Ministry of New and Renewable Energy. So we have got this funding, which has actually enabled us to do a lot of research in this field. And I would like to thank my colleagues and students at NCPRE who has basically helped me learn a lot about this particular technology. Okay, and I would also now end with some of the useful resources that you can actually look at. Of course, NCPRE website. This is an online book, PV education, so you can freely access this. Okay, and meaning it is focused on silicon technology, but it has theory, but also a lot of small videos, applets, that whenever they're showing some calculation, you can run some applets to see how things are changing when you change some basic parameters. Okay, and and a lot of things that for measurement and evaluation of solar cells modules. There are videos and so on. So very useful resource. It's all free. Okay, you don't have to pay for this. And then there is something called pvlighthouse.com.au. So this is also very useful. It actually provides the list of several online tools that are available for simulation of various things. Optoelectronic properties of materials, thin films, and so on and so forth. And then you can also access several free software, simulation software for simulating solar cells. There is also a simulator for simulating fabrication of a silicon solar cell, and so on and so forth. So very useful resource. Okay, thank you very much. Any questions if anybody has?
So,
So few questions
Sir.
has been given in the chat box, sir.
Sir,
The participants
is it
have
possible?
given some questions in the chat box.
Yeah,
just read out, ma'am. Read out to sir, no?
Yeah, sure, sir. Mr. E. Naveen Kumar has questioned that why bifacial is not commercialized, or what is the difficulty in manufacturing that bifacial solar cells?
yeah. So bifacial is commercial. Okay, so you can buy these bifacial modules in the market. Okay, so the only thing is that bifacial technology is still somewhat of a niche, and I'll tell you what is the reason. See, bifacial technology, you have seen you have to let the light into the photovoltaic module from front side as well as the back side. Okay, so which means that you have to have glass on the front as well as on the back side. But conventional silicon photovoltaic technology, you have glass on the front side and a polymer on the back side. So the polymer tends to be cheaper. So as a consequence, the bifacial module would be more expensive. Okay. Also, the processing, the way that it is being made, the solar cell, it is slightly more expensive to make bifacial solar cells. So overall, the cost of bifacial module is more than that of uh, uh, monofacial, meaning light coming only from one side. So cost is higher. Now, of course, cost is higher, but we are also getting some more energy from the backside. But the problem there is that I mentioned that the backside light that is reflected from the ground, right? If I'm thinking of putting up the photovoltaic modules on some structures in a field, for example. So this is what is reflected from the ground. Now you need to have fairly good reflection. Then only you get an advantage from the bifacial module, right? But then the ground has to be highly reflecting. So if you put it in a place where grass will grow, for example. So when the grass grows, it is green. Okay, it would not reflect too much of light. Yeah. So then I need to basically cut the grass, or I need to put white sand in these places. Uh, but it may be easy, for example, in some cases. For example, if I'm talking about a rooftop, and on my roof, the roof is flat, I'm putting up it on a structure, so I can paint my roof white. Many people already do this because you can get the temperature of the roof and inside actually goes down a little bit because some sunlight is reflected if you put paint it white. So or if I want to use this in some of the agriculture applications where some light going through the solar cell is actually good for me, right? So it's available but not as popular as monofacial because the energy yield from this is a little bit, meaning heavily dependent on the location where we are installing it. Yeah. And preparing such places and maintaining them can be expensive. Okay. So it is more like a commercial decision. Yeah. Technology is available in the market. You can go and buy them, no issues. Now there are, just a moment.
There is one more question from Dr. Ramarao Pokandi, sir. Whether is it feasible to have PV modules in electrical vehicles? That is the question asked by him, sir.
Yeah. Electric vehicles. Yeah, so there are two things, two possibilities here where you integrate photovoltaic panels on the vehicle itself. Okay. And one of the most famous examples of this is actually there was one entrepreneur, I think it's a French guy. He actually had built a plane. Okay. and then it took one round of the Earth, yeah, using this plane. Of course, he had some stopovers and so on and so forth. And there were some specifications. They actually said, you know, it would, of course, have battery. Okay, and he was flying alone. Yeah, it would have battery, but then the battery would be used only to support this for only certain percentage of the total hours of flight and things like this. So it is possible in that sense, but it was fairly expensive proposition. Now, if you take a car, okay, so people have done these calculations. If you have a typical car, and I want to, you know, I have to use some storage of this electricity. So if I put solar panels on the roof, I can get 20-30 kilometers of total thing if from that area. Okay, I can drive about 20-30 kilometers using the electricity I get from the top of the car area, if the efficiency of the solar cells is more than 30%. Okay, so people have done these calculations. The other possibility is, of course, you can, you know, you might have seen this. There are parking areas. Okay, people are parking this. So you cars, right? So the parking area is made with a roof made of solar cells, solar panels. Okay, and then you're charging. You go to the office and you park this under in such a place, and you plug in your car, and then you're charging this. Okay, so that is a possibility. And the black fly that I talked about yesterday, meaning yesterday I saw this YouTube video. So they have made, you know, the people who made them, they were parking the aircraft, small aircraft, in a shed, the roof of which is made of solar panels, and they are actually, you know, charging the batteries from this thing. So that is the other possibility, and which is in fact being implemented in many places already. Thermoelectric devices, yeah, that's a completely different topic, but it works on similar principles. Basically, you can get a voltage, you know, if I heat up a semiconductor based on similar principles. Okay, but the problem is that the efficiencies are not really very high in those cases, unless you go to high temperatures. So there are a lot of other challenges in this. But people are already using it in niche applications, not for large scale applications. Yeah, so meaning typically in sensors and so on and so forth. But then it's not at the moment, the efficiencies are not that great, and the costs are actually not justifiable for commercial applications. Okay, this is what I saw on the this thing, the chat window. Any other questions anybody has, please?
Sir,
I ran over time by, you know, now it's already, it's supposed to end at 11:30. So Arun, so
Sir,
if you want to stop now, we can stop.
we'll take one or two questions, sir. I think most two fellows are trying from the beginning. 1712, the participant, you can ask your question by unmute yourself. Once participant is, sir.
Hello?
Yes, sir. 17, sir.
hello.
Sir, you can go with one question, sir.
Yeah. Where is the question?
Yeah, is unmuting, sir. Is trying to unmute.
Okay. Yeah.
I'm Dr. Ramesh.
Yeah. Hi.
Good morning.
Good morning.
My question is a fundamental question, sir. Photocurrent, instead of photovoltaic, somewhere else in your slide you told that the current, the more sites of the material current is concerned, the voltage. Component of photovoltaic cells, like a photo. Question clear, sir?
No, I did not really get that. So what you're saying is that the current is low, meaning high voltage is low. What, I did not get this because there were some interruptions in this. While you were saying.
Photovoltaic instead of photovoltaic, it's a photo current.
Yeah.
Photo current.
Current. Yeah.
Somewhere else, in your slides, you told that the more the surface current is concerned, voltage. Can you just, so is a fundamental doubt, sir?
Why is it so? Is it? Why is it so? Is it?
Why is it so? Exactly.
Okay. This is, yeah. Okay, so there is, the answer to this is not very difficult, but then you need a little bit of background in this. So basically, we are taking a solar cell, right? Like this. Yeah, this is a 3-dimensional device. Okay. So what is happening here? You have, the sunlight is coming, right? And the current, we have seen that the current is proportional to the light, the short circuit current. Okay, so because you had that in the equation, more sunlight, you can imagine this, more sunlight means more photons and more electron hole pairs will be generated, and proportionately there will be a larger current. Okay, so if I actually increase the area of this, yeah, and color, okay, so if I use this, okay, so if I may actually do this and say, okay, this is my device is, I'm extending it. Okay, so right, so I have something like this, and so the area is increased, more photons are incident, and I would have larger current. Okay, because light is also falling here. Yeah, but on the other end, what you're doing is actually, if I look at it from a circuit perspective, right, what you're doing is, so this may be easier to understand. Let's say I take this. Okay, I take this small area solar cell. Out of this, I cut this piece. Okay, and let's say this has a VOC of VOC1. On the other hand, what are we doing? We actually, let's say that I take another piece. Okay, right? This is the other piece of the solar cell. This is the other piece, right? And this would also, this give me VOC2. They are equal, right? Yeah, because they are identical pieces. Okay, they have the same area, everything is the same. So what you have is like two voltage sources, two batteries connected in parallel. You get my point?
Right.
Yeah, they're connected in parallel. So the voltage of these are like some which is identical. So this would be, total voltage here would be, and this is equal to, let's say, VOC, and this total voltage, meaning here would be only VOC. They are not adding up. So I can actually add anything here, the area, this is not going to change. Okay, so this is kind of circuit perspective. The other thing is that if you look at the physics, Meaning this argument is very much valid. But if you look at the physics, what happens in the solar cell is that there's something called Fermi level, which you define in a semiconductor, which is dependent on the concentration of electrons and holes. Okay, there's a concept called quasi-Fermi level. So typically the voltage is dependent on the separation between the electron quasi-Fermi level and the hole quasi-Fermi level. Okay, so since this is a single material, that is really, just a moment. So this is now a single block, right? The quasi-Fermi level will be the same everywhere because it's a single block of silicon. The whole thing is, okay, it will not be different in different places. So the voltage, open circuit voltage, is not dependent on the area. Okay. So I hope this is clear.
Yes, sir. Yes, sir.
Yes,
Okay.
sir.
Yeah.
Sir, with your permission, of course, I have a second doubt, the last doubt.
Yeah.
You are taking, of course, diffusion. There. Why can't actually talk about the dispersive?
Which one?
You are talking about somewhere in the answer, some diffusion of atmosphere.
Diffuse component of light, right? Yeah.
Yeah. Dispersive. What actually?
What do you mean dispersive?
The scattering, sir.
Yeah, because this diffuse component comes because of scattering only. See, how does this happen actually? So this is because there is some dust particle, for example, in the atmosphere.
Exactly.
Right, a suspended particle. So this light is coming down like this, right? And now it is scattered. Okay. So it can be scattered in different ways. So it's basically, scattered this way or maybe whichever way. So all these things together, right? If I take all this scattered light, part of this can also be reflections from other places, surrounding structures. Usually you call that as albedo, but the scattered light, this is the scattered component. This is what is the direct component. Light that is coming straight down without scattering. So this is called direct.
Sir, my fundamental doubt is, of course, the white light. When actually in the scattering medium,
Yeah.
dispersive, we have the emergence of the color. So,
Yeah. See, that color thing would not. Yeah, you can see this, for example, if I have, for example, you have red color in the evening and all these things, right? In the morning.
exactly.
Yeah, but that's not usually. You would have, of course, the spectrum of light that you're receiving would
Exactly.
change from morning to evening. Okay.
Yeah.
That is also because of the diffused, the scattering effects. So the total energy received as diffuse and direct would actually change with time during the day. Okay, that is for sure. That is an effect which needs to be considered. Yes.
Okay, sir. Thank you, sir. Thank you very much.
Yeah. Okay.
Yeah, thank you,
Yes,
sir. Thank you for giving clear basic insights into the photovoltaic technology and elaborating the generations of solar cells, giving the facts and figures of the efficiencies, and also very patiently addressing all the questions raised by the participants, sir. And it really helped all the young researchers to move forward in the research work in photovoltaics, sir. Thank you. Thank you very much, sir, for being with us.
My pleasure. Thanks. Okay.
Thank you, sir. Thank you so much, sir. Thanks for
Yeah.
presentation.
Okay, Arun, so I would log out now.
Yes, sir. Yes, sir. I'll make the mail communication, sir.
Okay, thank you. Yeah.
Thank you, sir.
Yeah.
Thank you
Bye.
so much, sir. Thank you.
Bye.
Participants, the next session will start by in 10 minutes delay. Just take a 10 minutes of break and please come back. If you want to stay back, you can stay back in the meeting, participants. We can take 10 minutes of break. Then we will start the next session by 12:05. Please stay back. Don't leave the meeting. The second session will start by 10 minutes.
Nanoscience and nanotechnology is a study
Small video about that the speakers where he came from.
of the properties and applications of materials and devices which are very, very small. Obviously, this futuristic research requires a people from different traditional disciplines to come together. In IIT Bombay, this has been done by setting up a Center for Research in Nanotechnology and Sciences, which consolidates the nano research in IIT Bombay. CRNTS also took under its umbrella the Sophisticated Analytical Instrumentation Facility, or SAIF, which had existed earlier.
SAIF is a unique concept which was initiated and is being funded by the Department of Science and Technology, Government of a number of advanced state-of-the-art analytical and commissioned under made available researchers from to examine materials.
Least polluting of energy generation technologies. We are trying to make solar cells using metal oxides and silicon, and these films would be of extremely low thickness. And these materials can be further deposited using a variety of techniques, including spray coating, which is a technology used for painting cars.
The electricity which is derived from solar and wind has to be stored in its chemical form before being put to use elsewhere. Batteries and supercapacitors are energy storage systems which enable this. At CRNTS, we focus on properties of materials at nanoscale which can give us better energy storage systems.
We work on economically viable thin film solar cells. Our main focus is to develop new materials that can harvest solar energy by depositing layers of atoms one by one. In order to study various aspects of these thin films, like quality of the film, its elemental analysis, its abrupt junctions, we need highly sophisticated techniques like TOFSIMS and HRTEM.
Water pollution is a very critical problem in India. Some pollutants can even affect our health when they are present at trace levels. And some of these contaminants are not even removed by the traditional treatment processes. So we are developing tailor-made nanoparticles for removing these pollutants in the presence of sunlight.
In collaboration with environmental science and engineering, we are studying the structure and functionality of these nanoparticles. We are using sophisticated techniques such as electron microscopy and spectroscopy for this purpose.
Nowadays, healthcare nanotechnologists are trying to use nanomedicine to combat deadly diseases like cancer. This requires the generation of smart nanoparticles for efficient drug delivery in order to reduce the present treatment-associated side effects for better science. Characterization of such smart nanoformulations requires high-resolution electron microscopes and zeta potential analyzers.
Bone regeneration is a very complex and demanding problem as it has hierarchical structures ranging from few centimeters to few nanometers. Therefore, we have engineered bone graft for reconstructive surgery with advanced composite made from nanostructures having tuned parameters for easy clinical use. Environmental electron microscope has enabled us to study key cellular molecular interactions on the scaffold at a nano level.
I use time-resolved X-ray tomography. It is more of a high-resolution CT scan. It tells me whether rocks contain oil and gas. It is very useful to study microstructural evolution and to characterize materials.
Proteins are one of the most important biological molecules and essential for life. Proteins have unique, complicated three-dimensional structures that regulate their functions. So, understanding the structures of proteins is essential to solve several biological problems. In CRNTS, we are engaged in solving new protein structures using X-ray crystallography.
Material properties can be analyzed chemically on bulk or surface by bunch of instruments. Even slight change in composition can change the properties of the material, and this slight change can be determined by spectroscopic method at very minute level.
Carbon fiber epoxy composites can be used to make strong and light wind turbine blades. However, the interface between the epoxy and the carbon fiber is a weak spot from which damage can nucleate easily. Here at CRNTS, we are working on strengthening the interface using materials development and processing so that the wind turbine blades can have a longer life.
Wind turbine blades made of composite materials are the major components of a wind turbine system. And these blades are subjected to cyclic fatigue and environmental loads during operation, which leads to reduced life and degradation. So a collaboration between material science and aerospace department is envisaged to enhance the composite material properties and thus the design life of a wind turbine blade.
The output of these sophisticated instruments has any meaning only when the experiments are performed properly and the data are analyzed carefully. We ensure this by conducting weekly meetings involving users, experts, and operators, where we thrash out issues and ensure that the data are of highest quality. This serves users not only in our institute, but across the country.
Good morning and good afternoon, Professor. Biswajit, sir.
Yes, sir. My voice is audible, sir?
Yes, sir.
Yeah.
Can you hear me now?
Yes, sir.
Yes,
Your voice
sir.
is
We
audible.
can hear, sir.
Good morning, good afternoon, because
Good afternoon,
yeah,
sir.
I'm
So
ready
we'll
now.
start with a small introduction, sir. So, good afternoon, everyone. Welcome back to the second session of this FTP, and we are happy to invite the research person for this session, Dr. Mustafa Al-Kashani, CEO, Silicon Valley for Nanotechnology, Saudi Arabia. And sir is a co-founding member and CEO of Swissdar for Smart City Company, Saudi Arabia in 2018. He is also the co-founding member of Oslo National University, Jordan. Dr. Mustafa has did his bachelor degree in electronics and communication in 1993, then a master degree in solid state electronics engineering and artificial intelligence in the year 2000. Dr. Mustafa did his PhD in 2007 in microengineering and nanoelectronics. And he has many research papers in the field of nanotechnology and MEMS. Apart from that, he is the former training officer at Qatar Customs and Port Authority, Qatar, former quality manager at Jordan Free Zones Corporation, Jordan, and former consultant and instructor for quality standards of public education with King Abdullah bin Abdul Aziz Public Education Development Project, Tatwir in the Saudi Arabia 2010. He is the team leader for ISO 9001 for several years and the former member of SEMI organization, Semiconductor Equipment and Material International 2012. And with this a small introduction, I would like to give the session. I would like to hand over the session to Dr. Mustafa. Sir, please.
Thank you very much. Assalamu alaikum wa rahmatullah. I will be a good honor to be with you today, talking about the business and implementing best development strategies for operational excellence. My presentation will include definition of smart city, dimensions of smart cities, dimensions of smart cities, performance management, map approach, structure of map approach, activities map, and map approach in smart city system, characteristics of map approach for operational excellence, map approach versus other management methodologies, and finally, with the conclusions. Let us define the smart city. What's smart city? Smart city uses the Internet of Things, sensors and technology to connect components across a city to make everything for life easier, either for owning or using. Smart cities use connected technology and data to improve the efficiency of city service delivery, enhance the quality of life for all, and increase equity and prosperity for residents and business. So it's an urban area that uses different types of electronics methods and sensors to collect data. Insights gained from that data are used to manage assets, resources, and services efficiently. In return, that data is used to improve the operations across the city. This data collected from citizens, devices, buildings, and assets that is then processed and analyzed to monitor and manage traffic and transportation systems, power plants, utilities, water supply networks, waste, crime detection and information system, and so on. Dimensions of smart cities. Smart cities usually occupy 6 dimensions: people, technology, infrastructure, management, economy, government. Our presentation today will be with the fourth dimension, which is related with management. Smart city is closely related to the government services, whereas its administrative excellence depends on the management methodology used. Transport and traffic management also, energy management, healthcare management, water management, crime detection management, and waste management, and other service management. Now, any management is related to the methods of the performance measurements. So management performance is a system that enables the organization to define and focus the strategies, objectives, indicators, and actions that drive organizational improvements, and finally to reach the excellence. The good performance management system brings organizations' performance management data under one roof, allowing it to use its integrated features to gather, analyze, and communicate the information that measures its progress. By studying the performance data, the organization has information at their fingertips to decide the best course of action for its organization and to make sure that objectives are achieved. So the challenge here, how can we get the best performance measurement system? So measuring of the performance is the most difficulties which faces the organizations, and this causes the most of the fails which face that organizations and prevent them to achieve their objectives. So by choosing the suitable measuring system for performance can help us to clarify, document, and communicate our organization's strategy, ensure our strategy and objectives are cascaded from the corporate level to the individual level, monitoring, communicating, and managing statutory and local performance indicators through traffic lights, charts, graphs, and tables, assign ownership for key areas such as objectives, projects, and performance indicators and business processes, manage and monitor improvement projects, and understand the impact on the organization. Also help to provide an online system to communicate how our organization works from the highest level of strategy to the lowest level of operational detail. Implement and integrate standards and strategic plans. As a result, we can save the time and efforts by automatically collecting performance information from existing IT systems through the smart city system, automatically provide alerts on underperformance and missing information. So in order to achieve all of these abilities and to skip this challenge, we have a solution. By using my approach and integration it with our organization, our services, we can get all the abilities which we mentioned. So what's my approach? My approach is a method by which any organization, either the productive or the service introducer, can control and measure its performance accurately and numerically. That means the performance indicators, either the efficiency, effectiveness, productivity, echo of the product or service product's effects, response of the end customer, quality deviation, and quality can be numerically measured. in order to understand what's mean of ma approach. Ma is stand to a word of Arabic word. Ma. That which means what in English. So in any organization, for any system, for any policy, in order to ensure that policy or system is working well, we have to make auditing from time to time in order to ensure we are working on the right way. So in the auditing system, there is two types of methods in auditing. The first one is to focus on the results. So what is the level of the customer satisfaction in your organization? I'm focusing on the results of the customer with the customer satisfaction. If that result is satisfied, no need to go in details in order to save that time. But some of the other types, we are asking about the procedure. How can we achieve the customer satisfaction? Now, in the first question, which is the principles of my approach, we are focusing on the shortest way in auditing and getting the right result which are looking to. So, in order to understand more, let us talk about the meal. Now the time that your time is related or near for the lunch time. Here in Saudi Arabia, there is a very tasty meal called kabsa. Now, if anyone from any world come to the Saudi Arabia and ask the intelligence question, what is the kabsa? What's the kabsa? Now the question, the answer will be limited. The kabsa is the best and the most tasty meal in Saudi Arabia. So from the methods of the question, we can limit the methods of the answer. So I'm focusing on the excellency, on the by the question, I'm focusing on the quality of that meal. So when they answer us this the best meal, also that mean it will be with high quality. Now, if another one asks about the kabsa with the different meaning, with the different methods, how can you make the kabsa? This answer may be spent hours in order to explain how can we make the kabsa, and at the end we cannot get the quality of that meal, the taste of that meal. So maybe it will be shown or not, because I didn't focus on the excellency through my question. So what is focusing on the excellency, on the quality itself? For that, my approach is based on the shortest way in order to achieve the excellency and the quality of the performance. Now, the structure of my approach is composed from 7 items. The first one is the activity itself. In order to make that activity, we need inputs, requirements, and through the procedure with dealing with these inputs, in order to get the output, we have to use a monitoring and measuring tools to monitor the procedure. And in order to get a scientific or a parameters, clear parameters, we have to use performance indicators. My approach use 8 types of performance indicators: efficiency, effectiveness, productivity, response, eco, and the effect of the service or products, and quality. Now, from the view of my approach, any inputs will not be out of the 4 types of resources. These 4 types of resources are the human resources, informational resources, financial resources, and the infrastructure. Through my approach, we can get action plan for any activity. And from action plans, we can get the job description for all the employees, the organization structure, the budget, the key performance, the strategic plan. So in one methodology, we can get all the management parameters which any organization need of them. So now my approach initiates with analyzing any organization and get all the activities which are used on that organization, either the management, either the technical, either the core, the main, the secondary, and so on. So in case if we take any educational organization, we will analyze this organization upon the approach model into its main and secondary activities. So the main activities in any education organization, for example, teaching, educative administration, communication with the local community, measuring student performance, communicating with the students' labels, measuring the employee satisfaction, financial procuring, registration, curriculum development, auditing, and there's also management activities, employees attendance and absence follow-up, student requirements, student advisorship, healthcare development program implementation, official relationships, motivations, training, e-learning, transportation, and so on. Each of these activity will be built upon the approach standard or structure. So each activity will be determined what's the inputs, how can we use this input in order to get the output, how can we monitor the procedure in order to achieve the quality, and how can we measure the performance indicators in order to control it and develop it. So at the end, any organization, we can build the activities map of that organization. Now each block of this in this shape is represents activity, and as you see, the output of the activity will be an input for the next activity and so on. Now any defects on the output, on the service, on the main service, on the main products, any defects in any time will be a one for the manager, for the owner of the activity, and any defects will be shown from which activity was done in order to catch and control and develop it in the shortest time. So This approach with the smart city, if we apply this approach for all the services which is related with the smart city services, everything will be monitored and controlled accurately and can be avoid any defects in the shortest time. So my approach, applying on water management, water and healthcare management, which is related with the smart city system, applying with on energy management, on traffic management, governmental service, waste management, transport management, and all the service which is related with the smart city. By these methods, everything will be controlled and monitored, and we can get the excellence easily. So this is a general structure of using my approach with the smart city. As you see, all the services which is related to the smart city will be under control by using my approach, and all of these data will be transferred through the Internet of Things. So the characteristics of our approach, my approach is suitable for both the public and the private sectors, as it is easy and compatible with all educational and cultural levels of employees. The ability to understand it by simple educated employees is almost the same as it understood by senior management personnel, as both can deal with it with the same efficiency. It enables the organization or the individual to measure the following performance indicators. And this is the unique between the competent methodology. We can, by this methodology or approach, measure numerically the efficiency for each activity, the effectiveness for each activity, the productivity of each activity, the effect of the product or service provided to the beneficiary customer or the end customer, the echo of the products provided to the customer, the quality of the product or service of the organization, and for each activity also, and deviation of equality. Any deviation in equality in any time, it can be controlled. Through this approach, any organization can design and create the following management requirements in a direct and easy method without any complexity or additional costs. And these requirements are job description of the organization, the organizational structure, the budget, performance indicators and standards for all activities in the organization, and finally the strategic plan of the organization. Also, through this approach, the map of the activities of the organization is built, and a statement of the relationship of each activity with the other, so that it is possible to observe and measure the impact of the reactions of each activity on the other activities in the calculation of performance indicators. Through my approach, goals, objectives can be measured with high accuracy, whether that for targets or the strategic goals for objectives. Through my approach, waste can be controlled and monitored in all activities. Through my approach, it's easy and compatible with the working principle of the human brain, so it is easy to be applied and understood by all employees with all their different levels of education. It is easy to select and teach a management team for my approach. There is no need for a high level of education for those who manage, evaluate, or review the system applied for this methodology. Therefore, the cost of implementing my approach is much cheaper than other management methodologies. It enables any manager to understand and apply this methodology in any field and for any organization without the need to specialize in that field. It's appropriate and compatible with all models of the International Administrative Excellence Awards, as the methodology corresponds to the essence of any of them. Also, my approach depends on the use of an accurate algorithm methods in artificial intelligence to calculate the effectiveness, efficiency, productivity, and the quality of the products or service provided by the organization in full after the activities map of the organization is designed in its final form. One of the characteristics of my approach that distinguishes it from the rest of the other used competing methodologies is that the main evaluation process through this methodology is carried out by the employee himself in charge of the activity. The activity which called the activity owner, and the accuracy does not deviate from reality by more than 5%. What that means? For example, the tea boy who is responsible for making the coffee or the tea. The boss, maybe he is not familiar with making a coffee, but the tea boy, he is professional. Now, who can evaluate the activity or the process of making the coffee? Either the owner of the activity or the boss. The process itself. The tea boy will be the best person who can evaluate the process itself, because all the environments of that activity is under his vision. Now, when he evaluates that process, so he will give us the most accurate results. Some person may say that, okay, this process owner will give him, for example, high level of performance. No problem. As we see here, turn back. Let us come here. As we see here, the employee is one member of the HR who is related with the activity. And for example, any HR related with the coffee make, he will be the tea boy, the people who drink, the people who bring the materials for making the coffee, the sugar, and so on. All these people will be under the HR resources. And this will be one part of the inputs for the activity, as there's informational resources, financial resources, and infrastructure. All of these inputs affects on the outputs, affect in the efficiency of the procedure itself. Now, the HR, the evaluation, in case of that tea boy gave himself 100 as a performance. Now, this evaluation will not be the only evaluation. The evaluation of the employee, the tea boy, will become from himself, from his manager, from the stakeholder, from all the employees. Now, with using the artificial intelligence, any defects on the evaluation of that boy for himself will be already updated. So the final result will not exceed 5% of the final evaluation of that procedure. And this will be applied for all the activity. So any activity will be mainly evaluated by the activity owner himself. And any defects in the evaluation of that person, of that employee's evaluation, will be updated automatically by the approach automatically. Also, the evaluation team of my approach focuses its work on supervising and ensuring the accuracy of measuring performance indicators, and not carrying out the measurement process alone as is followed in the other methodologies. As we talked, now the evaluation team will focus only for what? The best or the most criteria or parameter for is the evaluation of the T-boy himself or the activity owner himself. That's all. Just you review the evaluation of that employee from himself, from his manager, from his end customer, and so on. But the other evaluation, it will be more accurate by the activity owner than that the team who is not well known with the environment and with all the inputs of that activity. So the accuracy of the work produced through my approach is distinguished, not to mention that the work effort assigned to the team of my approach is much less than that assigned to the evaluation teams for other methodologies. Let us talk now about my approach for operational excellence. What's the relation between my approach and the operational excellence? If we look at the all international or local performance awards of excellence, we find that all these modules or models originally based on the assessment of the activities of the organization. So my approach is the core of any model for performance award of excellence. And this means it is suitable and needed for any organization, either private or governmental, which looks for excellence. Let us take a look about the excellence model or the international excellence model or a global excellence model. As we see, any excellence model will focus on enablers and results. And through enablers and results, there is the innovation and learning. By learning the enablers, they can be or can give more innovation. More innovation will be better results. And in order to monitor and control all of these actions should be evaluation system. Rather, what we will talk about. Now, what about enablers? Enablers includes leadership, either the top management or the intermediate management. The people's stakeholders, either the employees, the customer, the resources, the suppliers, policy and strategy, partnerships and resources, and also the process. All of these will be fall down in the enablers. Now the results includes people results, customer feedback, the employees feedback, the stockholders feedback, people results, customer results, society results, and the key performance. As we see here, the core of this model is based on the processes and key performances, key performance. And my approach is already based on this. It's based on activity and key performance. Now, in order to measure or monitor the results of any management system, the excellence or the global excellence model use radar system. R stands for results, determine the results which required. A stands to approach, plan and develop the approach. D stands to deploy that approach. And A stands to assess, and R stands to review, assess and review approach and their deployments. So, determining the result required, aim for results aligned with the policy and strategy making process, covering all performance aspects such as financial, operational, and stakeholders' perceptions. Also, regarding the plan and develop approach, develop sound approach capable of delivering the results required for now and the future. Regarding deploy approach, D, deploy approach in a systematic way to ensure full implementation to cover all the activities and the process in the organization, and assess and review based on monitoring and analysis of the result achieved and ongoing learning activities. Identify priorities, plan and implement improvements where needed. This is a fast view about any excellence model in the world. Now, my approach, when we look about the excellence model and compare with my approach structure, it's already covered the core of that model, because it's focused on the key performance and the activity itself, which is the process. So my approach may be the best or the most suitable methods in order to achieve excellence in any organization. As you see, so here are the activity and here's the performance indicators. These related with enablers, these related with the results. And monitoring system, instead of radar, there is a monitoring system through measuring the performance indicator by numbers, numerically. Now, let us compare my approach with respect to the other management methodologies. As we know, from the management systems is Kaizen. Kaizen reduces the 8 wastes in overproduction, waiting times, unnecessary transportation, overprocessing, excess inventory, unnecessary movement, defects, unused employee creativity. In 8 location, in 8 for activity. Now, comparing my approach with Kaizen, my approach is more comprehensive than Kaizen methodology. Kaizen focuses on the waste in 8 processes or activities, while my approach, it measures the waste for each activity in the organization. So my approach is much more comprehensive than Kaizen methodology by at least 5 times and more accurate. Why 5 times? Because the most of the organization have at least between 30 to 40 activities. Now Kaizen focus in 8 activities will be 1/5 of the 40 activities. So my approach is more comprehensive by at least 5 times and more accurate. My approach versus balance scorecard. As we know, balance scorecard measures key performance for the main targets of the strategic plan of the organization, while my approach is measuring all the key performance for each activities which are composed the targets of the strategic plan, because the small parts of each target plan for the same organization is already composed from the activities. As each target is including many activities, for this reason, my approach is more comprehensive by at least 5 to 8 times than balance scorecard. Let us talk about total quality management. Total quality management, there is 14 principles, but ISO talk from it 8 principles. Customer focus, total employee commitment, process approach, integrated system, strategic and systematic approach, continual improvement, fact-based decision-making, and communications. In my approach, these parameters or these features, some of the activities which my approach cover and control it. So my approach is the best or the most accurate or comprehensive methods which is related with total equality management. Now let us talk about Six Sigma. As we know, Six Sigma focuses on one path per each project. For that, it's very expensive because the criteria of Six Sigma is very high. It's very high. While my approach focuses on all the activities at the same time. Its rights is not in the same criteria of accuracy, but more comprehensive. The overall implementation of Six Sigma in any organization is very costly, while my approach is very cheap with respect to that. Six Sigma is very, very cheap. Six Sigma needs very smart employees, very intelligent employees, high educated employees, while in my approach need normal employees. Six Sigma is not suitable for service enterprises or enterprises with small industrial productivity, in which the daily reoperation rate of the process is low. While my approach is suitable for all types of industrial productivity or service introducer organization. So, by comparing my approach with the other management methodologies, we find my approach is cheaper, is simpler, easier to use, and more accepted with all types of the people, because it is very near for the methods of the brain. So it's very suitable for all types, all levels of the employees, from the T-boy till the top management. As a result, smart cities system should be based on a good management system in order to achieve the excellency. If we have a very high technology, but we have no good management system, we cannot get and achieve our goals. So the good management is the main parameter, or from the main parameters in order to achieve our strategic goals. My approach is an accurate and clear methodology for measurement of the performance indicators, and not only the familiar or the popular performance indicators. My approach is unique to deal with 7 to 8 types of performance indicators. The most of the performance indicators in the world, we are talking about efficiency, effectiveness, and productivity. While my approach, we are talking about 8 or 7 types of performance indicators, which lead to measure the quality by numbers. By measuring the performance indicators, the quality of the performance can be achieved and controlled, which will lead to excellence or excellency. My approach is a suitable methodology for the smart city system, as it can be easily used for any organization through the internet, and the cost of using this application is relatively very low with respect to the others. With my approach, the accurate and numerical management of the smart cities in all the world will be easy and available. Thank you very much for your listening, for your attendance, and I'm ready for answering your question. Thank you very much.
Thank you, Professor. Few questions in the chat box also. Dear participants, you can unmute yourself also, you can post the questions.
What's the question, please?
Yeah. How the variations of pressure in water delivery measured in the water supply systems, the networks of Saudi Arabia and near real time. So, like, how the various pressures are measured in the water delivery systems, which is in the real time.
With respect to this methodology, I didn't get your question, please.
Yes, sir. How the various pressures are measured in all the locations in the water power supply systems, which is you are following in the Saudi Arabia.
Yeah, regarding my approach, I'm sorry to tell you that I'm very busy with the nanotechnology and MEMS technology. I don't have enough time in order to register this approach and to keep our intelligence for that. We applied this for 3 associations, one in 2012 and one in 2015. But till now, I didn't announce about this methodology. As I told you, I don't have enough time because this approach is already created by me.
Yeah, thank you, Professor. Any other questions from the participants?
I have already put in the chat. Kaizen is for manufacturing industry. Can Kaizen be applied for energy and water system networks, which are operational in nature?
Yeah. Kaizen, as I told you, is focused on reducing the waste in 8 activities or 8 places: overproduction, waiting times, unnecessary transportation, and overprocessing, excess inventory, unnecessary moving defects, and unused employee creativity. My approach can monitor and measure any waste in any activity. So it covers the process of Kaizen, but with more comprehensive.
Okay.
Okay.
Yes, sir. Thank you, sir. Any other questions you want to discuss with sir? It's an open for discussion. If you have any clarifications on my approach, like
any question, I'm ready.
yeah, I think no other questions in the chat box. We can participants. If you are not having any questions, shall we conclude the sessions? Any queries? Yeah, I think no other questions. Then we are in the point of concluding sessions.
Okay, thank you very much.
Yeah, thank you, sir. Thank you so much. Your wonderful presentation, which you are the MA approach is how it is going to be utilized for the smart cities, and we are wishing you that like at the next level the smart cities can be implemented completely if you are going for the MA approach. Without we can energize and we can reduce the wastages. You have explained it very well, and it is very clear to us. Thank you, Professor. Thanks for your valuable time is sparing with us. Thank you so much.
Thank you for, okay, thank you very much for organization with this and to give me the opportunity in order to be with you. Thank for all the audiences. Thank for all the listeners for us. And I got honored to be with you today.
Sure, sir. Thank you, sir. Once again, thank you, sir. Thank you so much.
Okay. Okay, you're welcome.
Participants, the feedback links are available in the chat box. Please complete the feedback link. The next session, as per the schedule, will start by 3 o'clock. So it's now lunch break for all of us. Thank you, one and all. Thanks for your patient listening. Thank you, sir. Thank you, participants.
Well, moving on now, smart cities are the future of the cities in the world. The idea of smart cities rests on the idea of using sophisticated technology to solve civic, transportational and environmental issues which affect all cities of the world. Prime Minister Narendra Modi launched this ambitious program in 2015 to ensure that India catches up with the world, and through Smart Cities program, cities of next generation could come into effect. Here's a report.
Urbanization is a non-ending phenomenon. Today, 54% of the global population live in cities, which could reach 66% by 2050. This will add another 2.5 billion people in the cities. In India, 31% of the current population lives in cities and contributes 63% of the GDP. By 2030, 40% of the Indian population would live in cities, contribute 7% of the GDP. Hence, cities will continue to be the engine of growth, productivity, innovation and creativity of the modern world. It then becomes important for India to reorganize its urban space. In 2015, Prime Minister Narendra Modi launched the Smart Cities program. The government released a list of 98 cities, including 24 state capitals, which were to be developed as smart cities. The question: what constitutes a smart city? Has a fully developed transport system with last mile connectivity. The internet reduces the cost of services and provides solutions for civic problems. The smart city concept is based on the internet, which provides solutions to citizens through smartphone applications. Urban heat is reduced through architectural style, and open areas bring communities together. Built-up areas create walkable localities, reduce congestion, air pollution, and boost the local economy. Smart cities have an efficient and eco-friendly system of collection and disposal of waste. And importantly, a smart city generates its own resources and uses it for the benefit of the population. The Smart City project has a huge reach. 15.2 million citizens participated in the project, accounting to 12% of the Indian population. 45% of the mission's money comes from the centre, which stands to the tune of 2.05 lakh crores. But there are big challenges also. Over 3,700 projects are still grounded. Out of 2 lakh crore, only 9,500 crores so far. Bengaluru has used 7.4 crore of 94 crore allotted for work. Thiruvananthapuram spent 4.5 crores from 194 crores available. Kochi has used 38 crores out of the 198 crores set aside for the city. The centre now wants to expand the Smart City project to 4,000 cities. India also lacks town planners, which are required for building new towns. The centre believes that the investment in urban areas can work wonders for the Indian economy. The Smart City project can be the New Deal of India, which pulled the United States economy out of recession in the 1930s, when the US decided to increase public spending and build massive urban infrastructure. Whatever the result be, the Smart City program remains one of the key focus areas of Prime Minister Narendra Modi.
And with that, it's a wrap on this edition of the Bulletin, but you can catch all the action